then the part C, let me bring in another anti-derivative problem, another indefinite interval. And by the way, I should have mentioned, at this point in our learning, so now you're going to start hearing me using this term, integrate. Okay? It's a verb, right? It's an action, but so what it means here is really, it means taking the antiderivative. So when you hear me say integrate, right, and you can start using that term too. That means we take the antiderivative. Right? So integrate f(x) means we take the antiderivative. You want to say no? Because otherwise, if we're doing a definite integral, then I'm going to say integrate from somewhere to somewhere. Right? But just integrate itself, it means it's an indefinite integral. It means that we integrate without bound, so it turns out to be an antiderivative problem. Okay, so now we still want to evaluate. We still want to integrate this function. Let me look at our integral. Okay, that's it. That's it. X squared is here. I'm having 4x cubed plus 1 dx. So let's integrate that function. So again, throughout all of these problems, allow me to suggest a substitution, and then on your own time at home, you feel free to give it some try, right? On the different substitution, because there's no right or wrong substitution. So the one I want to suggest here is how about we taking u equals 4x cubed plus 1. Okay. Taking u equals 4x cubed plus 1, and so in that way, here's how I'm seeing it. You can go du dx, right, equals a 12x squared by taking the derivative of u. Okay. So you guys learned that problem because that style yesterday. So now we're going to rearrange, because by allowing this to be now a fraction, to be regarded as a fraction of the two differentials of the u dx, right? And we're now talking about we can rearrange that fraction here. This equation that involves the differentials. So we got du over 12x squared. I can divide both sides by 12x squared and multiply dx on the other side. So we're looking at the du over 12x squared equals dx. Now I can see that now I have also created for myself or produced for myself a substitution, right? That can substitute for the x. So now we are getting ready for putting all the pieces together. So as far as putting the pieces together, the integral is here. Now our substitution was chosen for that 4x cubed, so the 5x squared right now stays the same, right? So we're looking at 5x squared times the square root. But inside the square root, the entire expression now becomes u, right? And then the dx in our expression here, right? And it's a product connecting between the function with the differential dx. So the dx now is substituted by du over 12x squared. Right? And so at first we thought, because remember I introduced those checkpoints of questions, right? Those checking points of questions so that you can ensure that you're on the right, doing the proper thing. So we were asking ourselves, we were checking to ourselves whether we have get rid of all the old variables. And so it thought, and for a moment, we thought we didn't, but now at this point we realize, hey, we can cancel the x squared away, right? And then we'll bring that 12 as a coefficient with the 5 there, so we end up with a 512, right? And divide that, and multiply with the square root of, and multiply with the integral on square root of u du. Okay. And so, did I make the problem any simpler? Or any easier? Yes, I did, right? Now it's simply just a 512 times the integral of u to the 1/2 power. Now we're ready to integrate that function. The function here is simply just u to the 1/2 power, so the power rule is going to kick in just fine. Right? All right, so in that way, our final answer is going to come out. I mean, our integral for this function comes out being 512 times, right? And then 1/2 plus 1 gives me a 3/2, right? And then a 3/2, when we take the reciprocal, is going to give me a 2/3, right? Times u to the 3/2 power. We're adding the constant c. And then once again, we definitely don't want to stay at that final variable being u, right? So we want to bring back our original substitution. So making it, it's going to be a 4x cubed plus 1 raised to 3 halves power plus c, and then we have a coefficient in front here. So the 2 cancel with the 12 right here, giving you a 6 in the denominator. So it's 5 over 18. Okay? That's our final answer. Okay. So now, guys, I want you to take your own time a little bit, papers and pencils, and go ahead and verify that we have found the correct antiderivative. We have found the correct integral. And you know, I've been mentioning how we can test. The only way to test, right, is take the derivative here. Take the derivative of your answer, of your final integral, and then as long as the derivative falls right back into that beginning function, we know that we're done. So after taking this derivative, are we ending up with 5x squared times the square root and 4x cubed plus 1 inside? Okay. So that means we know that because I'd rather that you guys be comfortable and be fluent with that process again. Because when you're done with any antiderivative work, right, a lot of times it's good that you check your answer again. That's the only way. Right? And so that's because be ready for when you take the exams or anything like that. Now you don't have to include that checking steps on your solution. But make sure you do that on scratchbook somewhere so that you can ensure you got the correct answer. Okay. All right. And so example 1 is about done. We got through a few problems where you can see that it's still easy to recognize the substitution here, right? So a lot of times when you have an expression, what rings a bell at the end of this example 1 is that a lot of times when you have those expressions that stays even inside of powers, right, or inside of root, we tend to grab the whole expression inside the root, right, to be a substitution. But I'm just saying that we tend to. Big majority of time it works that way, but I'm not saying that it's 100% always going to have to be like that. Okay, and so that's example 1 as one class problem. So before I head out for example 1, before I head out to the next example, and it's still just doing substitution, and we get learning more the experience right here. But now we can unlock a couple things here. Back in the early days, when I was showing you about the antiderivative, I remember we had this little formula here. And then at that time, I kept apologizing you guys that I have to slow your thinking down a little bit. But see, think about e to the ax here. Dx, right? When we take the antiderivative, I wrote down back then as a formula, right? What was that formula? Do you guys remember? The answer to this is what? The indefinite integral for that is, anyone remember? Put it back to pages if you want to. I mean, it's not a test. I'm not testing you. Huh? E to the ax, right? Did you say over a? Yeah. So can I write that as 1 over a, right? From d to the ax. So back then I only asked you to take that as a formula. See what I'm saying now? Okay. But now with this rule that you've learned, now I believe someone also whispered to my ear at that time that you can substitute, but then I wanted you to hold on to your thought because now it's the right time to come. Right? Everybody learned that here. But see, you can easily substitute u for ax. Beat that. See what I'm saying now? I mean, think of the a simply as just a coefficient with the x. Right? So we're substituting u for we let u to substitute for ax. So it's a choice of the substitution. So du dx, taking the derivative of this in terms of x, right? You need just a constant a. You guys following? Right? So that means rearranging this differential equation, right? We have du over a equals dx. Sounds good? Right. So for this integral now it becomes so that means that the integral e to the ax dx, right, will becomes putting the pieces together, it becomes e to the u, right, and dx is substituted by du over a. You guys follow me on that still? So that's why now we're looking at du over a means it's 1 over a times du times all of these, so I can put 1 over a in front, right, of our integral. So the integral has become surprisingly a lot. So it's just the antiderivative of e to the u. And what's the antiderivative of e to the u on its own together? Just e to the u, right? Multiplying that 1 over a in front plus c. And so your final answer, and of course we don't want the u here, so our final answer, one more step here. 1 over a times e to the ax plus c. That's how we have now formally proven our quick little result. Right? Back then we tried to remember it as a formula, but now it's really, there was a reason why it did that. Right? There was a reason that led to that. And so let's, I'm not going to call these an example yet, but I'm still going to introduce a couple other problems here that's common enough to later on it's going to start becoming something that you can do quite natural over here. Quite natural over here. Okay, so everybody knows that antiderivative or the indefinite integral for 1 over x has to go into a natural log of absolute value x, right? Let's see, you guys follow it? Okay. And so think about this as a more general problem. What about you're asked to integrate the kind of function where it's 1 over, right? Some linear expression, like say ax plus b. So see there are variables all over now. You want to say ax plus b, and then you want to integrate. You want to take the antiderivative but in respect to x, right? So that means x here is your main variable, and this is coefficient, and that is a constant term. Sounds good? So at this point, in the strategy that we've learned, in the method that we've learned, what can we do for this problem? We're going to do a substitution, right? So now why don't I let you guys decide a substitution? Right, letting your mind work for here. Right? This could be easy enough, and you've seen me doing work often enough. So what's a good substitution here? Or what could be a working substitution? What's that?
Ax plus b.
Ax plus b. Okay, I'll take that. No judgment, right? No judgment. You know what I'm saying? And then once it works, it will work. So du dx as a consequence, right? Will come out being the derivative of this. Taking x as really the variable, these are just coefficient and constants, right? So taking that derivative gives me just simply a. That's following, right? And so that means rearranging this equation of the differential over here, and we're looking at du over a, right, equals dx. Please, am I going too fast with the algebra? Right. So now we have perfectly found all of the substitutions that we need here. So putting the pieces back into the function. I've substituted the ax plus b, he did, right? 1 over u. See that now? Okay. And then the dx here is substituted by du over a. You got the idea? Right. So we checked ourselves, did we substitute away and wash away completely all the x variables? Yes, we did, right? Did we make the problem easier, right? And easy to recognize? We did, right? This problem is nothing but just 1 over a times the integral of the function 1 over u du. So it's just exactly that. Other formulas, right? Except for we're working in terms of u now at this point. Now it becomes your final answer here for this integral 1 over a times the natural log of absolute value u plus c. Okay? And then 1 over a, that means 1 over a times the natural log of ax plus b in absolute value plus c. So yes, this problem here, this kind of problem happens often enough to the point that people in these days even take that as a formula, as a quick. You guys, it will stay with you guys as well. Trust me, as you work with that often enough, it will stay. But the point is, antiderivative for ax plus b, right? 1 over ax plus b, or the integral of that, it's going to simply come out being 1 over a times the natural log of ax plus b in absolute value plus b. Then you can see this in every textbook there. Now it belongs to the pocket reference. All right, so let's even go further. So now I'm going to get back on my other board. I believe this board, if you will write some more notes on that. All right, so let's call that now example 2. We want to evaluate the integral again. Still rushing a little bit. So now, before I head into an example, okay, what about a definite integral? So substitution method in my teaching approach, right? I tend to start out and I tend to focus on using that for an indefinite interval, right? For an antiderivative, that's the plan with that. But then actually we can also effectively use this method for definite interval as well. Those with the upper and the lower limit. Okay, so now let me bring out a problem. So just think about a problem like this. When we are asked to evaluate, right? Calculate, and then how about from 0 to 1, right? Here we got a 2x times the square root of 1 minus the x squared, for example. Okay? dx. So let's look at a problem like that. Okay. So this is clearly different with the earlier problems that we've done. Right? The earlier problem was an indefinite integral, or simply just an antiderivative. But here it's a definite integral. So now I understand that a lot of times, I mean, for many students, they try to do this. I mean, before I teach, they think of doing something like this. Yes, we let the u right here. What can you suggest for a u, by the way?
1 minus negative 2.
Okay. Yeah. Along with that similar experience with that, right? You can pick that thing inside the root. Right? So 1 minus x squared. Trust me, when you've done these often enough, right? And you set yourself into a good way of recognizing a good working substitution here. So that's making it minus 2x, right? For the derivative of u. You guys following? Okay. And then we rearrange that into a du over minus 2x, right? Equals dx. Okay. So I've seen a lot of students doing this. Right after that substitution point, they kind of branch out and treating that as an indefinite integral. So the indefinite integral version right here, right? The indefinite integral version goes the 2x, right? 2x times the square root of 1 minus x squared. Whoops, that should now be a u, right? And then the dx here is substituted by du over negative 2x. And so the minus 2x cancel with that, right? And then making it a negative integral, right? And the square root of u, or I can just at your level here, write it as u to 1/2 power du. You guys all good with that, right? So they treat the problem entirely as a indefinite integral. So it's a minus, right? And the 2/3 right here times u to the 3/2, right? Plus c, and then we bring back the original variable. And so it's going to be minus 2/3, right? And then 1 minus x squared, we have plus c. So they found the antiderivative. And then they make a conclusion. So that leads to the definite integral from this, right? For 2x times square root of 1 minus x squared dx. Okay? And that's equal to the minus 2/3 times 1 minus x squared in parentheses to 3/2 in here. All that there, evaluate it. Here we can skip the plus c, right? Evaluate it from 0 to 1. See what I'm saying? Now, so it's okay that you branch out as one complete separate work with this, right? And get the antiderivative separately. And then come back to that beginning definite integral and write it down in that foundation that's set out by the fundamental theorem of calculus. See what I'm saying? No? So after getting the antiderivative separately, and we go, hey, that definite integral equals this antiderivative evaluated at the 2 points, right? And then you're going to start doing the substituting it. See what I'm saying? No? All right. So this work right here is completely legal. The work here like that is legal, but it's a little bit long. So you make your choice on whether you want to go that way. Okay. That's going to be a method that's even more direct. Still, the substitution method a little bit more direct. We don't have to do like this, meaning we don't have to go through the antiderivative separately, but we can do it all in one step here. So think about it. If you make u equals 1 minus x squared as your choice, right? Then these are the limits in terms of x, right? So when x equals 0 right here, when x equals 0, so we tend to call it u1, meaning the low, right? So 1 minus 0 squared, giving me a 1. You guys following? Okay. And then we call that u2 right here, right? Or giving 1 minus 1 squared, right? Or 0. Sounds good, right? So this is the extra substitution that we have produced as well. So when we substitute, we're not in a definite interval, right? after we made a substitution, we're not only substituting for the variable and the d expression, we're also conveniently substituting away the two limits again. See what I'm saying now? And so by doing that, here's the nice consequence here. The integral starts 0 to 1, right? 2x square root of 1 minus x squared dx. Yes, it becomes the integral from 1 to 0. Right? It looks a little strange like that, right? It looks a little strange like that, but it will work. 1 to 0. And then the 2x didn't get a substitution. Let's leave it there, square root of u for now. Right? And then it's going to be a du over minus 2x. You guys follow it? And then just the usual thing right here. We cancel out the 2x. We're left behind. We got left behind with a minus, right? So it's a minus integral. The minus the definite integral from 1 to 0, right? Then square root of u du. And so now you think about the impact here. I'm going to be moving on completely in terms of u. Completely in terms of u. So this integral here, by the way, you can rewrite that as a u to the 1/2 power, right? Du. You see a minus sign right here? That minus sign is going to cause an effect that we can switch the integral bounds, the integration interval around. So now I can turn it into a 0 to 1 like that. Right? And the minus sign cause that effect. Remember that property we've done? Anytime that we switch the order, right? The interval of the integral interval, then they related by the negative relationship.
Because you took out the negative.
It's yeah. So, or I don't want to explain that as I took out the negative. That's one way of seeing that. It just means when you have negative here, right? It caused this integral order right here. Switch around. You see, it was 1 to 0, right? Here, switch to 0 to 1. Yeah. But then, if you ask me why I want to go with this flipped version, it's just more naturally we want to see the low numbers being smaller, right, and the higher number being larger. See what I'm saying?
What I'm also wondering is like the step above it was from integral 1 to 0 or 0 to 1.
Yeah. This is the original one.
Right.
This is the original one in terms of x. It happens to look the same. This is what it was in terms of x. So when the integral was in terms of x variable, right? We were integrating from 0 to 1. And then once we make that substitution, the 0 over here is equivalently to 1 in the u variable, in terms of the u variable. You see the change there? Right. And then the u2, which is where you substitute that 1 into your substitution, and you're coming out with 0. That's why when you're putting that into the interval in terms of u completely, you put this is the u1 right here, and that's the u2.
Got it. Okay.
You guys following with that right there?
Yeah.
Okay. I hope I cleared that up now. So it's not, yes, it looks it's a little bit denser, so it's looking the same, right? So it may have caused some confusion because the two numbers, they look so alike, but they are from completely different worlds. Okay. And so everything we're doing now is in terms of u right now, even including these variables. Okay. I mean, including these limits. Okay. Maybe even though the numbers look the same. And so now you all ready for the fundamental theorem of calculus. All you do now is just that integral will come out being the antiderivative for u squared. I mean for u to the 1/2, right? It's going to be a 2/3, right? U to the 3/2. You don't need to plus c, and then you can just directly substitute in 0 to 1. You know what I mean? And that now is making it 2/3 times 1 to the 3/2. And then we're subtracting 2/3 times 0 to the 3/2. Right? That's how we get our answer. So that's the answer to 2/3 on the end. Right? Yes. So now you can tell me which route is longer. The earlier route when we went separately with the antiderivative is longer, right? It's definitely longer, but of course it's not illegal, right? It's not illegal. It's completely okay that way. Now, allow me to do something like this that point out what's illegal about this. But you know what? I shouldn't apply that problem to this. I shouldn't apply the thing in this problem, because for this problem, after we change the variable, it's still looking so alike. So you guys don't see what I'm about to deliver. Let me use a different example here. Okay, so let's switch over to this board of mine. Let me point out another demonstration problem here as an example, and you can see how dangerous it is to do things like this. Okay. So it's not a formal example yet, right? But you already hopefully learned a lot of work out of this. So how about an integral from 0 to 1 again? Okay, but your function is a 2x times e to the x squared plus 1, right? Yeah. Okay. Anyone would like to help me suggesting a u substitution? X squared plus 1. I'll go with that. No judgment, right? Don't worry. I'll go with anyone. And if it doesn't work, we're gonna all switch plan together. Okay. So x squared plus 1. So x squared, when u equals x squared plus 1, then du dx, right? The derivative comes out being 2x. Right? And that means du over 2x equals dx, all due to that understanding that we're now taking this du over dx here as a fraction of the two differentials, right? And so we rearranged that equation of the differentials. But now, in the meanwhile, at the same time, this is the dangerous work that my students have done right here. Very dangerous. Okay. Don't do this. They do integral from 0 to 1. Okay, 0 to 1, and then 2x times e. See, they putting in the 2x and then e to the u, and then times du over 2x. Every substitution is doing just fine, and but they treat that completely as a definite integral with the original boundary, original limit. Okay, and then they carry it on. So the 2x canceled out, as you guys have already seen, and from 0 to 1, right, as an e to the u, du, and then they keep evaluating that further, making that an e to the u, and then substituting in 1 and 0, so e to the first power minus e to the 0, which is e minus 1. Okay, the answer is going like that. The answer is just an algebraic expression of that. But what's incorrect about this is that this is not the derivative. I mean, that's not the integral for. That's not the integral limits for your integral in terms of u. See what I'm saying? So when you get to this point, you cannot use these two numbers anymore. As a matter of fact, what are the two numbers that the proper for that? See, u1 being the low, right? Got to be when you substitute 0 into your substitution right here, it's ending up with the 0 squared plus 1. So that number down here must be correctly 1. See what I'm saying now? The correct one here is 1, right? And then the u2, the upper u, you go 1 squared plus 1, because when x equals 1, right? 1 squared plus 1 equals 2, your upper number here needs to be 2. That's the correct version of that. See what I'm saying now? So, the reason, I mean, a lot of times they did this, and then they have to overforce themselves. They have to force themselves to remember that this is for x, this is for x. See what I'm saying now? So and this is what I mean. They force themselves to put put 1 and 0 and 1 here, and they force themselves to remind themselves that, hey, e to the u here, get an antiderivative, and then bring back the e to the x squared plus 1 like that. Okay, and then evaluating from 0 to 1. Now, this is correct, but you see, you force yourself too much, and there's a risk that you mistakenly substitute these into your antiderivative. See what I mean? That's why, I don't recommend doing that at all. Right? And I'm being telling that in your learnings at the very early days, so don't try to come and argue with me that, why not letting me do this? I'm preventing that risk that you can make error. See what I'm saying now? Right? So stay away from that. Right? If you decide to go with u, go completely in terms of u. Right? If you decide to just find your way to go only in terms of x, and say in terms of x. Right? But don't do the halfway thingy again, right? All right. And so with that problem, are we ready for seeing a couple examples here? A couple example problems. So that's how easy it is that we can evaluate a definite integral using the substitution method. So now let's look at example 2. Evaluate. All right, so in the first problem, let's evaluate the integral, definite integral from e to the 9th of dx over x times natural log of the square root of natural log of x. Okay, so we spend some time writing it down. We're going to get started. Okay, so now let's get in, shall we? All right, so I can take some suggestion from somebody about what we could substitute here. And then no judgment in terms of being right or wrong. So, right, so I'll take u equals natural log of x, and to get no judgment. So a substitution is just a substitution itself for here. And so now, here's how I'm seeing it. So, once we have made our substitution, and at this point right here, what matters is simply just a substitution. Again, no right or wrong. So, from here, du dx, we've learned from our calculus 1 that it's going to be 1 over x function. And now I can quickly rearrange this du dx. And at this point, we've learned that this is now not only a symbol for derivative, but it's a fraction between two differentials, du and dx. So I can rearrange this as du now multiply that x to the other side, so x times du equals dx multiplied to the other side equals dx. Okay? All right, and so now this is what our integral becomes. So by far we have substituted, and again, there's no right or wrong. So I'm going to rewrite it as the integral. Now dx here is substituted by x times du. In the denominator here, we didn't make a substitution for x. So again, we're leaving it there. Then the square root. The natural log of x inside the square root is now substituted by a u variable. Okay? And so, but now keep in mind that our integral from beginning here is a definite integral. So we need to, and these two integral limits right here, they are in respect to x. So now we need to also change them to some limit values in terms of the u variable, in terms of the new variable u right here. So how about I'm going to call the upper integral limit right here to be the u2. So that means what? Our substitution here, u is equal to natural log of x. So when x equals e to the 9th, right there, specifically I'm going to substitute that into the natural log function, and that will come out here in precisely 9. So u2 is 9. And then u1 is where I'm going to substitute x equals e right here into our natural log function, making it natural log of e. Right? So natural log of e comes out being exactly 1. So that's our lower limit, the lower limit of our integration, the interval, in respect to u, of course. And so now let's proceed further. Right? So this integral now, we're on our way to rewrite things in terms of u now. And so the upper limit is now 9, and the lower limit is now 1. Right? And then now this variable that we didn't choose a substitution for that earlier, that we didn't make a substitution for that earlier, now I realize that we can just cancel with the other x in the expression. Okay? And so now at this point we have successfully arrived at an expression where we have du over square root of u, okay? And then the integral here, the definite integral here will go from 1 to 9. Okay? And so everything at this point, now looking back at our checkpoint question here that we're talking about, we have completely washed away the old variable, the x variable, and then everything now is in terms of u. And then the next question we're asking ourselves, we're checking ourselves, have we made this integral here easier to handle? Well, think about it this way. We can rewrite the integral as an integral from 1 to 9, and then we have seen this quite often before. We're going to rewrite this as u to the negative 1/2 times the du. And so now that is obviously a lot easier to handle. Okay, and so now we can just go ahead and work on this problem here, quite, very similar to how we've done that in our past learning. So here the antiderivative fundamental theorem of calculus is ready for action here. So we're looking at u, now negative 1/2 plus 1 is making it a positive 1/2, and then 1 divided by 1/2, okay? And then that's the antiderivative. We need to evaluate that from 1 to 9. And by the way, needless to say, let me spend one more step here rewriting that to clean up that antiderivative here. So that's making it 2 u to the 1/2, and then we're going to eventually evaluate from the expression from 1 to 9. Okay? And so now, at this point, the next step is simply going to be just 2 times 9 to the 1/2 power, because I substituted the upper limit 9 for u, okay, in terms of u, into the antiderivative that we have currently found right here. We are already found to this point. And then again, the antiderivative there, I'm going to substitute in the lower limits for u. So u equals 1, substitute into the antiderivative to the 1/2 power. Okay? And so now at this point right here, the answer will come out. So 9 to the 1/2 power is another way of saying it's a 9 to the square root of 9. So that's making it 3 times 2 is 6, minus, now square root of 1, or the 1/2 power of 1 is 1, right? 2 times 1 is 2. Our final answer comes out as easily as 4. Right? So that's how we doing this this first problem in our example 2. Any question for me? So now we can see that at this point, I was saying that earlier, there is no judgment of right or wrong into this substitution that our classmate here has decided for us. And so now we made it with that substitution that we didn't have to change anything. We made that all the way to the final answer, nice and easy. So guess what? This was a good substitution. All right? Part B, integral from 0 to your function is sine of 2t dt. I'm seriously getting tired of the x variable, so I switch over to t. And so with this one right here, I think the integral, the substitution is so easy to recognize, right? You want to suggest a substitution?
The 2t.
The 2t? Yes. That one. No judgment. du dt equals 2. That means du over 2 equals dt. So yes, it's just my style that I want to show you guys that we kind of find a direct substitution right into that dt again. Okay. So now u1, the low is going to be just 0. The high here, u2, is going to be just 2 times pi over 2, right? Making it a pi. Okay, so the integral now becomes something like this. Still from 0 to low, but pi. Right? As we change, these are each of the u variable. Sine of u, right, times du over 2. Good. So now we can rearrange this and making that a 1/2 times sine of u du, right? Evaluating from 0 to pi. So your antiderivative for sine of u is minus cosine of u. So I'm looking at minus 1/2 cosine of u, right? And we're evaluating that from 0 to pi. Okay. Now, so negative 1/2 times cosine of pi minus, and then there's a negative 1/2 times cosine of the 0, right here. Right. And then the answer can come out usually being 1 altogether.